Hello students. In previous video we had defined plane of vibration, polarized and unpolarized light. We also did define plane of polarization, which is perpendicular to plane of vibration. And we also saw a property dichroism exhibited by some crystals. Now in this video we'll see Malu's law, which talks about intensity of polarized light when it comes out from some analyzer. So let us start. Now we know that there are some crystals which allows only some light waves and absorb other light waves. Which light waves are allowed? In which electric field vectors are oscillating in particular direction, and that particular direction is determined by that particular crystal. Such crystal is tourmaline plate. So in tourmaline plate, there are optic axes. There are certain axes, certain direction, along which if light falls, uh, those electric field vectors will be allowed. So suppose if this is optic axis of this tourmaline plate, what it means is that this crystal will allow only those light waves in which electric field vectors are oscillating in this particular direction. So, what if I incident this type of light? What this indicates? This indicates that electric field vectors are oscillating in all different planes. But then what is the role of this crystal, tourmaline plate? It will not let all the waves pass through it. It will allow only this type of waves. So, on the other side, we'll see light, but only those waves in which electric field vectors are oscillating in this particular direction, and hence this light is called polarized light. This is unpolarized light because electric field vectors are oscillating in all possible planes. Now what if I allow the polarized light to pass through uh, one more tourmaline plate? So let us consider one more tourmaline plate in such a way that it is having its orientation of its optic axis along some different direction. So let us assume that this is the optic axis of the second tourmaline plate, and this is the line of propagation of the electromagnetic wave. Now when these waves reach here, when they encounter this plate, there is some angle between these two. If it is theta, then what will happen that this particular electric field vector or direction of oscillation and the direction of the optics axis, as they are at some angle theta, only some part of this wave will be transmitted. So this electric field will be divided into two components. This is E sine theta component, and let this be E cos theta component. So here if I say that electric field intensity is I0, which is proportional to E0 square, then on the other side of this tourmaline plate I will get this type of electric field vectors. And what is the value? It is E0 cos theta. What is theta? Theta is angle between these two optic axes. Now even though both are same tourmaline plate, identical in nature, but the role or job of this one is to polarize the incident unpolarized light, so we call it polarizer. Whereas this one is telling us in which direction the light is polarized. So we call it analyzer. But keep in mind both are tourmaline plate, identical in nature. So now, if I check intensity of transmitted light, if we label it as I, it is proportional to E0 cos theta whole square. It means that I is proportional to E0 square cos square theta, and initial intensity, this one, is proportional to E0 square. So what if I take ratio of this two? I by I0 is cos square theta, and then I is equal to I0 cos square theta, and I is proportional to cos square theta. Basically, this is Malu's law, that the intensity of transmitted light from an analyzer is directly proportional to square of cosine of theta between the two, polarizer and analyzer. So if these two, uh, if polarizer and analyzer are placed perpendicular to each other, then this transmitted light will be zero, and transmitted light will have maximum intensity if the two optic axes are parallel. So that is all about Malu's law. It gives us intensity of transmitted light from analyzer. Thank you.